Hello and welcome back to Planet Nibiru. Today we're going to discuss something most people think they understand, but probably don't. Plus, you'll learn a math trick that will blow your mind. It will have you asking, why isn't this taught this way in school? And for that, I have no answer. I think it should be. What are we talking about? Binary math. Binary math is the way that ancient Egyptians and other ancient cultures used to calculate. It's also the way that computers calculate. And if you calculate this way, you will never need to worry about multiplication or division ever again. No times tables, no long division, none of it. So let's take a look. If you ask anyone on the street what language computers speak or what code they use to compute things, they'll probably tell you binary code. Well, anyone who is familiar with computing will tell you that anyway. And that is correct. Computers use binary code to compute. Well, what does it mean to compute? If you look in the dictionary, it says to calculate or reckon a figure or an amount, especially when using a computer. It also says to make sense of or to make something seem reasonable, as in when someone says, that does not compute. In computing terms, binary code means everything is represented by a 0 or a 1, or a series of those numbers, and we'll get back to that in a second. Many people also equate binary code with Boolean, and though they're very similar, they are not exactly the same. Booleans means having two possible values, which is very similar to binary, but in Boolean, it's true or false. Of course, binary means having two possible values, 0 or 1. So these two definitions can kind of be interchangeable when you drill down on it, but as defined strictly, they are different. What almost nobody in the world knows is that computer language, or binary code, is really the easiest way to represent and calculate things mathematically. Further, almost nobody in the world, with the exception of computer scientists, know that this type of math has been used for thousands of years. The ancient Egyptians used binary math to do all of their equations, and we certainly know that the Egyptians were into precision. Hence the pyramids, with all of their impossibly accurate geometrical equations. We often marvel at the precision with which the Egyptians and other ancient cultures created things. But what we are not taught is that they were using the same type of math that modern computers use, giving them access to the same level of precision that we see nowadays. Well, what is this math? Well, I'm glad you asked. Math, as we know it, is based on the powers of 10. So as to represent the number 513, we know that we have 5 100s, 1 10, and 3 1s. So it's written out as 513. But what we are really saying is 5 100s, 1 10, and 3 1s. Computer language is based on the powers of 2. So all things are represented by numbers that double endlessly, starting with 1, then 2, 4, 8, 16, 32, 64, etc. So let's look at some simple numbers represented by our math and by computer math. Let's take 17. In our current system, that is 1 10 and 7 1s. In computer math, it would be 1 16 and 1 1, or 1 0 0 0 1. The reason that computers use this math, as opposed to our system based on 10th powers, is that a computer is a machine. Hence, it's very dumb. Now, many people will gasp and argue that computers are brilliant and they never fail, blah, 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 blah. Well, that's incorrect. Computers, like all machines, are dumb. They can only do what we tell them. The only thing they understand is yes and no, or true and false, or 0 and 1. Now, to be totally transparent, what they really understand is electricity or no electricity, and that's it. That is why we use binary code, being a 0 or a 1, because that is how we represent electricity or no electricity. If it's a 1, then it gets electricity. If it's a 0, it gets no electricity. So, to a computer, the number 17 is represented by electricity, none, 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 electricity, or 1, 0, 0, 0, 1. Pretty cool, right? I think so, but it gets even cooler, because computers don't have multiplication tables. They cannot understand the logic of multiplication. Matter of fact, they can't understand any logic at all until you get way on down the road to where we are nowadays with computing and teaching them logic, teaching them intelligence. But this is an artificial intelligence. It's not a real intelligence. It's what we program. Now, multiplication tables must be remembered by us because they are a construct that we made up in order to do math in the 10th power. When you were in the 3rd or 4th grade, you started learning multiplication tables or times tables because we decided a long time ago to use the 10th power as our basis for human math. But let's look at how a computer handles multiplication and how you can use it to your advantage, and you'll never have to remember times tables or multiplication tables ever again. First, let's be sure that we understand that any number can be represented by the power of 2. So, starting with the first number, 1, we have 1, 2, 1 plus 2 makes 3, we have 4, 1 plus 4 makes 5, 2 plus 4 makes 6, 1 plus 2 plus 4 makes 7, 8, and so on. So any number, no matter how large, can be represented this way in the 2nd power. So in order to multiply the way that computers do, and the way that Egyptians did, all you have to know is how to double numbers and how to add 2 numbers together. Sounds pretty easy, right? So let's take a look at a simple problem. Let's multiply 17 by 25 like a computer does. On the left, we have the table that's built out for the first number, 17, which we've already seen is represented by a 1 and a 16, or 1, 0, 0, 1 to a computer. On the right, we simply double that number as many times as we need to match the left column. So on the right, we'd have 25, 50, 100, 200, 400. Now we look at the numbers that are circled on the left, and then we go to the right-hand column to the corresponding numbers and we circle them, and we add them. In this case, it's a 400 and a 25. So the answer to math problem is 17 times 25 equals 425. And it's that simple. Nothing to memorize, no borrowing from the larger tenth, no carrying the remainder, none of that is necessary. Now, you can do the same thing with division. So let's try it out with this equation. 1075 divided by 25. This time, we're going to start on the right, and we will write out the numbers as 25, 50, 100, 200, 400, and 800. Now we're going to stop there because to go any higher would be to create a number larger than we are dividing. The next number after 800 would be 1600, which would be much larger than 1075. So we stop just before that at 800. Now on the left side, we make our table for the first numbers to match the numbers on the right. So we start with 1, 2, 4, 8, 16, and 32. Now, everything is aligned, and we know that 1075 is equal to 800 plus 200 plus 50 plus 25. So we circle those. Now we'll look at the corresponding numbers on the left, and we'll add them up. And we have the circled numbers of 32, 8, 2, and 1. Added together, that is 43. 32 plus 8 is 40, plus 2 is 42, plus 1 is 43. Now, of course, we could check that on a calculator, but we don't really need to because we know it's going to be 43. No long division, no borrowing, no carrying, none of that is necessary. So now we can see that a computer represents 43 as 110101, or electricity, electricity, no electricity, electricity, no electricity, electricity. Now, all of this gets way more complex down the road because we use these same series of ones and zeros to represent everything visually, like an image or a video, but at its core, everything boils down to these simple equations using the powers of 2. Even if you go into higher math like fractal geometry and you learn about things like the Mandelbrot set and how it is infinite, and it's the perfect set, and you see how this math is used in nature at every level of our existence, from the microscopic to the most infinite. This simple doubling of possibilities represents everything, even life itself. Okay, now that's taking things a bit to the existential extreme, but it's certainly true and very interesting. I find it very interesting and fulfilling to research. So thank you guys for all your support. Please like, subscribe, and comment, and don't forget to follow us on Twitter, friend us on Facebook, or swing by our website, t-shirt, or Amazon store for the best gear on the web. Thanks again, and we'll see you guys in the next video. Well, what does it mean to compute? If you look in the dictionary, it says to calculate or reckon a figure or an amount, especially when using a computer. It also says to make sense of or to make something seem reasonable, as in when someone says, that does not compute. In computing terms, binary code means everything is represented by a 0 or a 1, or a series of those numbers. This way, you will never need to worry about multiplication or division ever again. No times tables, no long division, none of it. So let's take a look. If you ask anyone on the street what language computers speak or what code they use to compute things, they'll probably tell you binary code. Well, anyone who is familiar with computing will tell you that anyway. And that is correct. Computers use binary code to compute. And we'll get back to that in a second. Many people also equate binary code with Boolean. And though they're very similar, they are not exactly the same. Booleans means having two possible values, which is very similar to binary, but in Boolean, it's true or false. Of course, binary means having two possible values, 0 or 1. So these two Today we're going to discuss something most people think they understand, but probably don't. Plus, you'll learn a math trick that will blow your mind. It will have you asking, why isn't this taught this way in school? And for that, I have no answer. I think it should be. What are we talking about? Binary math. Binary math is the way that ancient Egyptians and other ancient cultures used to calculate. It's also the way that computers calculate. And if you calculate Hello and welcome back to Planet